Welcome to week 13. This is your instructor, Dr. Todd Daniel, and this week we're going to talk about describing relationships using correlations. You know, there's an interesting correlation between storks and babies. Think about everything you know and have heard about storks and babies. You know, in Denmark, there's a positive correlation between the number of nesting storks in an area and the birth rate in that same area. So what do you conclude from that? Well, if you don't understand something very important about correlation, and that is that correlation does not imply causation, you might think that storks bring babies. But there's a better explanation. You see, in Denmark, when couples want to start a family, they move out of cities and into the suburbs. And the houses where they live in the suburbs have these steep angled roofs. Now, the storks prefer those steep angled tar roofs that are present on the houses in the suburbs because it's better for the storks to build their own nests. So yes, there is a correlation between storks and babies, but not a causal link. And so what we're going to talk about this week is what is correlation, and we're going to sort out the difference between correlation and causation, correlation and experimental design, and then figure out how to compute correlations. So correlation really means relationship, and mathematically it is a way of measuring the extent to which two variables are related. To get your mind wrapped around what correlation is, think about how do you know if you are in a relationship with another human being? A fundamental component of a relationship is that when you do something, the other person responds. When they do something, you respond. There's this interaction between the two of you. Now, there's other relationships or pseudo-relationships like stalkers who think that they're in some kind of relationship with a movie star. It's just that the movie star may not even know who this stalker is or may not be aware of anything the person is doing except when they do something really creepy and try to get into that person's house. You see, one person thinks that he's in a relationship, the other person, the movie star, does not. That's not a relationship. If you're in a relationship, you know that if the other person says to you, hey, you know that thing you did the other day, that kind of hurt my feelings and I hope you wouldn't do that again. And you say, oh, I'm sorry, I didn't know. I won't do that again. One person does something and you respond. Or you say, hey, do you want to go out for dinner tonight? And the other person says, that sounds like a good idea. Where would you like to go? And you say, well, I was thinking sushi. And the other person says, yeah, sushi sounds really good. Let's do that. That's a relationship. One of you does something, the other person responds. The same kind of thing occurs with variables. What we want to know is what happens to one variable when another variable changes. And if there is a relationship between those two variables, we'll say they're correlated. There are three things that can happen when one variable changes. The other variable could go up, we could have more, it could increase. It could go down or decrease, or it could stay the same, be unaffected. If the change in the second variable is an increase or a decrease, that means there's a relationship, there's a correlation. If it stays the same, then we say there's no correlation. So let's think about a variable like temperature. We are running the concession stand at the football game, and we know it's going to be really hot this weekend. So what happens as temperature goes up to the sale of cold soda? As the temperature increases, the sale of cold soda also increases. We could say those variables are correlated or related. They have a positive correlation. On the other hand, as temperature goes up, as it's going to be in the 90s this weekend, what happens to the sale of hot chocolate? It goes down. It decreases. So we see less hot chocolate sales when the temperature is high. When the temperature gets low, it decreases, and the sales of hot chocolate would increase. They move opposite of each other. What happens to the sales of foam fingers that fans might wear as the temperature goes up? Well, probably nothing. So there's no relationship between the sale of foam number 1 fingers. There is a relationship between cold soda and temperature, hot chocolate and temperature. Now, it's important to remember that correlation does not imply causation. There's not necessarily a cause and effect relationship. There could be. When variables are causally linked, when one is causing the other one to change, then we will also see that in a correlation. But just because you see a correlation doesn't mean that one variable is causing the other to change. There could be a third variable at play. There could be another variable that has not been measured, that's not even in your model, that's affecting both of the original variables, causing both of them to change. For instance, we know there's a very strong correlation between night and day. If it's daytime right now, in about 12 hours, it's going to be nighttime. So what we know is there's a strong correlation, but does that mean that day is causing night or night is causing day? No, they're both caused by the rotation of the Earth around the sun. And even if there is a causal link, we can't be sure of the direction of causality only from the correlation. The correlational coefficients that we're going to use don't tell us whether X is causing Y or Y is causing X. All we know is that there is a relationship between these two variables. Let me give you some other examples like this. The ownership of high-definition television sets correlates with increased deaths from coronary disease. So does that mean that watching television causes coronary disease, or the ownership of televisions cause heart attacks? What's a third variable that could be at play that would affect both of these? Maybe something to do with a sedentary lifestyle, where someone lies on the couch and watches a lot of TV and eats Cheetos and doesn't exercise. That variable might explain both of these. Or, as the number of bars in a community increases, there's an increase in the number of churches. Does that mean that with all those sinners, we need more churches? Or does that mean that with all those religious people, they'll just drive you to drink? What's the direction of causation? Well, actually, there's probably a third variable that explains both of these, and that would be population. As the population in a community increases, you get both more bars and more churches. Another thing you may have heard about is smoking and lung cancer. What we can say for sure is that smoking is correlated with lung cancer, but we can't say definitively that smoking causes lung cancer, at least in human beings. Now, why is that? Because we haven't done an experimental study. And why not? Because it would be unethical. So let me explain the difference between correlational and experimental designs. In an experimental design, the researcher manipulates an X variable and then measures what happens with the Y variable. In a correlational design, there's no manipulation. We simply observe the variables as they occur. We make no attempt to manipulate either one. If I wanted to test whether caffeine causes the jitters in human beings, could I do that, and could I do it ethically? And the answer is yes, of course. I would randomly assign people to be in one of two groups, maybe one of three groups. One group gets caffeine or coffee, the second group gets decaf coffee, and the third group drinks water. And we see what happens to the rate of jitteriness, or maybe we measure their performance on some kind of test. What we could determine is that caffeine has an effect on performance and how different levels of caffeine cause that effect. Now, could we do the same thing with smoking? Could we determine that smoking causes cancer in human beings? Not if we had to randomly assign people to smoke. You got to smoke a pack a day, and you smoke a pack a day of clove cigarettes, and you don't smoke at all, and so we randomly assign a group of people to smoke even though they weren't smokers originally. You see how that would be unethical and wrong, and we shouldn't do that. So we can't definitively say that smoking causes cancer in human beings. We can say that smoking causes cancer in lab rats, because lab rats exposed to cigarette smoke do develop lung cancer. But we have to be careful about what we say with correlations and causation. Now, what we can also say is that the preponderance of the evidence shows us that the strong link between smoking and cancer, and the mechanism by which we see cancer being caused as the result of cigarette smoking, as it occurs in lab rats, and that same mechanism we can see occurs in human beings, we can make some pretty strong statements, and we could say for sure that smoking is not good for you and probably is going to lead to cancer in a lot of people who smoke. So we want to be sure that we're not simply making a leap of correlation to causation. We always want to have enough information to justify the decisions that we're making. Now, correlational research depends upon linear correlation, and linear just means line. So it's where correlation can be graphed onto a straight line. So linear correlation describes a linear relationship between variables. What you see here is a scatter plot. It's a plot between height on the x-axis and weight on the y-axis. That straight line that you see is called a regression line. Now, in the next chapter, we're going to talk about regression and what it's used for. All we need to know for now is that we can put a straight line through the middle of those data to describe their relationship. The closer that those dots are to the line, the stronger the relationship.